Section number 2 is going to start talking about the subatomic particles. If you remember back, we talked about Democritus, we talked about Aristotle, and we talked about John Dalton and some of their early classification attempts at what an atom was. Now, as technology progressed, again, subatomic particles were found in an atom. So the atom was going to be progressing in what they knew at that time. We left off with John Dalton and his atomic theory. And again, if you think about what he said about the atom, again, he had those points to his hypothesis about what the atom was. Basically, what he said was an atom was a hard, dense sphere. Basically, it was like a shot put. Again, if you cut it in half, the inside's going to look like the outside. The outside's going to look like the same thing that's a third of the way through. So everything about the atom was exactly the same. Now, William Crookes comes along in the early 1800s, and I'm going to tell you he doesn't completely come up with anything about the atom, but what he did is he gave us a piece of equipment that scientists use to come up with their discoveries of an atom. But what he did was he had tubes that he hooked up to a battery or an electric charge, and when he hooked up those positive and negative terminals, he noticed that there was going to be a spark or a little bit of light near one of the ends of the tube. What he said was, the cathode end, this was the end that was connected to the negative terminal of a battery. And the anode was going to be the end that he hooked up to the positive end of the battery. So if we go ahead and look here, we're just going to say that this is my positive end, and we're going to say that this is my negative end down here. So again, the cathode end was going to be your negative terminal, whichever one is hooked up to the negative portion of the battery, and then the other end is going to be the anode end. And again, that is the portion that is connected to the positive terminal of the battery. Now the thing is, again, the CRT, this is going to be called a cathode ray tube. And basically the reason why it was called a cathode ray tube was, whichever end was hooked up to your negative portion, the charge always started towards the negative, and what it did was it flowed towards that positive end. Okay, so it always started at the negative end and flowed over towards the positive end. While examining these charges, again, as I talked to you earlier, I drew on the diagram, it was discovered that these charges always flowed from negative to positive. Okay, so always the negative terminal towards the positive terminal. And again, that's the reason why it's called a cathode ray tube. Those rays start at the negative end or the cathode end of it and travel towards that anode end or the positive terminal. With the work of this cathode ray tube, scientists learned a couple of things. Number one, cathode rays were actually a stream of charged particles. Okay, and again, because it was a stream of charged particles, that's what was going to allow scientists to start looking at different charges associated with an atom. And then the thing also was, because they started at that cathode end, the thing was they had a negative charge. Okay, so the particles were charged particles, but again, that ray itself was going to be negatively charged. The exact value of that negative charge right now is not known. J.J. Thomson comes along in 1897. So about 100 years go by. Like I said, Crookes was around 1800. And in 1897, J.J. Thomson was working with the CRT, and he discovered what is now known as the electron. So J.J. Thomson discovers the electron, which the electron is just going to be any negatively charged particle of an atom. So the first subatomic particle was going to be an electron. So all of a sudden we've now disproved what John Dalton said, where he said it is the same all the way through. So we have now an electron in this atom. Now, while working with the cathode ray tube, Thomson placed a magnet near the end of the cathode ray and noticed that there appeared to be this bending. Instead of this ray starting here and coming all the way straight across, the thing that he found out was this: that particle, instead of going straight across, actually bent down towards that magnet. So it did not flow straight across. Now, why he used a magnet, I don't know. Again, you've always heard of that fable or that story about Newton sitting underneath an apple tree and an apple falls and hits him in the head, and he says gravity is discovered. Well, same thing here. I don't know why he decided to put a magnet there, but again, maybe a magnet just happened to be there, and again, instead of flowing straight across, he noticed that it bent down towards that negative. Still started at the negative end, and still was trying to come straight across to that positive end, but like I said, it bent down towards the magnet. So what he did was he measured the amount of bending that occurred, and what he did was he developed the charge to mass ratio for an electron. Okay, so J.J. Thomson finds the electron, notices that there's this bending that occurs, measures the amount of bending, and said, you know what, we have a ratio between that charge and the mass for that electron. Robert Millikan, 1909, so about 10 years go by, and what he did was he looked at the work of what Thomson was doing. And what he did was he advanced what Thomson said, looked at that charge to mass ratio, and using an oil drop experiment gets the true value for what an electron is. His oil drop experiment basically looked like this. It was a two-chambered vessel where this little thing up here sprayed a bunch of oil drops into this vessel, okay, or into this upper chamber. Now, most of the vessels ended up collecting on this plate up here, but the thing was a few drops would end up falling down into this second chamber. Again, they knew the value of gravity, and again, as an oil droplet comes in, it's going to end up falling down to this plate. Well, here's the thing. If you look real closely, it says here that this is a positively charged plate. This one down here was a negatively charged plate. So what he did was he adjusted the voltage between the positive and the negative plates. And the thing also that I should tell you is this oil drop that's falling, or all of this oil over here, all of these oil droplets are charged. So what he did was he adjusted the voltage in these positive and negative plates, and instead of falling, he would get an oil droplet suspended in midair. What he would do is he would make some calculations on it. He would figure out how big it was. He was able to determine how many charges were on it. And by all of that information and knowing the voltage that it took to stop it, he was able to come up with the value of an electron. So again, he isolated an electron on those charged oil droplets, took some measurements, and calculated the charge on an electron. The charge of an electron now is known as negative, because again, electrons are negatively charged, but negative 1.6 times 10 to the negative 19th, and that capital C is just going to stand for coulombs. C-O-U-L-O-M-B-S. So the charge of an electron is known to be negative 1.6 times 10 to the negative 19th coulombs. J.J. Thomson followed quickly right after Millikan. Again, he knew that atoms were not completely negatively charged, because if they were just all negative, everything that was positive, they would be attracted to it. And again, he knew that that did not happen. He knew that an atom had to be electrically neutral. So the only thing that's going to cancel out a negative is something that's going to be positive. So again, working with that cathode ray tube, he found out that there were protons in an atom. Okay, so again, as I said, they were electrically neutral, so he determined there had to be something that was oppositely charged, or an opposite charge of the electron. And he named it a proton, which is just going to be your positive subatomic particle in an atom. Knowing of the proton and the electron, Thomson developed his atomic model of what it looked like. Again, here's his model of the atom. He said that these protons were completely filling up this space here. Okay, so again, notice I have this large positive charge in the middle. And what he said was all of these electrons were going to be spread here and there throughout the atom. Again, at his time, he called it the plum pudding model. Today, it's probably more commonly referred to as the chocolate chip cookie dough. When you think of making up chocolate chip cookies, again, you mix up everything associated with the batter, and you kind of get this yellowish mixture. Well, that yellowish cookie dough, that's your positive filler. Those are the protons, or that is the complete proton charge that Thomson was talking about. Now, all of a sudden, you take the bag of chocolate chips, pour it in, stir it up, bake your chocolate chip cookie, and each little chocolate chip would represent an electron, where the cookie portion is just going to represent your protons. Lord Ernest Rutherford came around in 1911, so only a couple of years after the work of Millikan and Thomson in finding those protons and their electrons. And the thing is, he studied the work of Thomson and his model of the atom, and he said, you know, we can't have this complete giant positive in the middle, because he did this gold foil experiment, and what he wanted to do is he wanted to study the effect of positive alpha radiation. Because if you're saying that atom is positively charged, meaning that most of that atom is made up of that positive charge, he said, well, it should repel anything or something else that was positively charged. So he did this gold foil experiment. And basically this is what it is. Again, if you remember what I said, this in here was completely positively charged. So again, this thing here, positively charged, had a little hole where the positive radiation could escape out. It's going to transmit itself in a straight line, and if you follow that straight line almost goes all the way through. When he looked, there was a particle that reflected back. There was a particle that reflected back here, and a few particles out here that reflected. But most of the charge ended up going straight through. So what happens to a few of the particles? Again, I said a few of the particles were reflected and a few of them were deflected. So Thomson could not be correct by saying that there was this positive filler in the atom. Because if I bring a positive charge towards something that has mostly a positive charge in the atom, it should cause the majority of these to bounce backwards. But it did not happen. And again, the key thing is going to be to remember that this ray coming here is positively charged. So he said, let's look inside an atom. Lord Ernest Rutherford was able to conclude two things about an atom. Most of the atom was empty space. And again, the reason why he said most of the atom was empty space is if you go ahead and follow this particle, again, notice it gets close to that center and bounces off. Okay, but follow this one here, ends up going straight through. Follow this one here, goes straight through. Follow this one here, goes straight through. So most of those particles were traveling straight through. And again, that would not happen if this thing was almost all positively charged. That would not happen. Again, if this thing was mostly positive, this particle should come here and end up bouncing back. The second thing that he found out was that positive charge that Thomson said was completely spread out. He said that all of that positive charge was going to be packed here in the middle. Because again, as I stated, okay, so let's go ahead and put this positive charge right here. And again, what he stated was, okay, so if this is positively charged here, and it's all of a sudden coming right towards that center, all of a sudden it's going to deflect and come down or change its direction of path. Follow this one here. If I follow this one here, it's coming right at the center, never gets to the center, and actually bounces back. The only thing that causes repulsion is something else that is positively charged. So if we stay away from the center, that positive alpha radiation went straight through. And that's the reason why he was able to conclude most of that atom was empty space. But those particles that were coming almost right at the center of an atom caused deflection to occur. He said instead of having that positive or those protons completely spread out, he said that they had to be packed into the center. And again, what he called that center was a nucleus. So it caused Rutherford to change Thomson's model of the atom. So what he said was, instead of being completely spread out, we've got the positive core, or those protons, are all packed here in the middle. On the outside are going to be all of your electrons moving around that positive nucleus. Again, Rutherford changed Thomson's model of the atom by placing all of the protons into the center, called the nucleus, and having those electrons moving around the outside. So Rutherford's model had a nucleus with electrons moving around it. The last piece of the puzzle came in 1932. Again, James Chadwick, he looked at an atom and realized that not all of the mass was being accounted for. They knew that electrons were small and had very little mass. He knew that protons were very large, but we had a discrepancy in the mass. And the mass, or the rest of the mass, in 1932 came from the neutron. And he said this neutron is a neutrally charged particle of an atom that has almost the same amount of mass as a proton. So here's what our current model of the atom looks like. We have our protons that are positively charged, and they are going to be located in the nucleus of an atom. So your protons are going to be in the center of the atom, or in the nucleus. Neutrons are also going to be in the center here. So neutrons have zero charge associated with them. And on the outside, and you have to think three-dimensionally, think of a sphere, think of a beach ball, and place in the center that nucleus. But again, three-dimensionally or spherically shaped are going to be these electrons moving on the outside. The nucleus, this is the center of the atom that has the entire mass of the atom. On the outside, this is going to be your electron cloud. The electron cloud is the area surrounding the nucleus that holds the electrons moving in multiple levels. Another way of saying this is each one of these could be considered orbitals. So we've got electron cloud, we've got orbitals. Also, we could call it energy levels if you want. So we have our nucleus that contains our protons and our neutrons and all of the mass of the atom. On the outside is going to be your electron cloud, which is going to contain the electrons in multiple levels in an atom. So if we go ahead and look here. A proton, here's its true mass, 1.673 times 10 to the negative 24th grams. But again, that is an extremely small thing. But if we use the proton and we use the neutron as relative masses, again, since they have the entire mass, we're going to say that it is 1. The neutron, like I said, again, 1.673, 1.675. Again, you can see how close these are to one another. So again, they are really going to be equivalent. That's why, again, I'm going to say that the neutron's relative mass is going to be the same as a neutron. The electron, here's the thing, it's about 2,000 times smaller. If I take a person and I put them on a scale and the scale reads 150 pounds, they weigh 150 pounds. That is kind of like the protons and neutrons. But if I would take a paper clip, okay, so if I take this paper clip here and place it on someone's shoulder, or that 150-pound person as they're standing on the scale, guess what? The scale is not going to change what it reads, because again, that paper clip is so small that it is not going to have an effect on the mass. The mass of an electron is 9.11 times 10 to the negative 28th grams, or like I said, it's about 2,000 times smaller. So what do I want you to know? Well, I want you to know protons are positively charged. They're in the nucleus of an atom. Neutrons, those are going to be neutrally charged, and again, they're going to be located in the nucleus of an atom, and again, these two have the largest mass. Going around the outside of the nucleus in those electron clouds are going to be your electrons, and again, they have basically no mass at all, and like I said, they're about 2,000 times smaller than the other two.